Hello, community. We have quite a number of methodologies for the next AI generation, but we also have new rules. And we will talk about in-context learning and test time training for domain shift specification, how to optimize your smaller language model in a cost-effective way. So we start exactly 1 month ago. Massachusetts Institute of Technology published this paper here on the effectiveness of test time training for abstract reasoning. And what they told us here, and they referenced here to test time training and in-context learning, they told us here, we found analyzing here the performance that the most crucial component here for a successful test time training of our LLM is we have an initial fine-tuning on a similar task of our LLM that we now encounter here in our inference. And for the in-context learning they specify, this in-context learning model, they don't always work out of the box for novel tasks. And you might say, yes, of course, if you have seen my last video, because now we understand the inner workings of ICL and TTT, and today we will make an even deeper dive into how does it work, when to apply what, and given your specific data set, if you should go with ICL or TTT in the inference run. So I showed you already in one of my last videos here, we have here a beautiful GitHub here for this MIT methodology, and this is the complete script that you need to run and validate here the results by MIT. But let me just bring a little bit of order in this and let us have a structured view. So what we have our LLM. LLM has been pre-trained by some global corporation or by your compute cluster if you only have a very dedicated expert LLM. And then there was here a supervised fine-tuning happening if you forgot a specific domain knowledge in your pre-training and you had to add a domain knowledge here to your LLM. Unfortunately, today, we still have here reinforcement learning here, this alignment process that the model behaves in predefined way by the global corporation. And this brings here some problems because currently, these alignment limitations are so strong that we see that hallucination happen and simply mistakes by our LLMs. But the most important part is if we run inference, and you see here, this here is inference, and we will look at two methodologies here for a deeper understanding, for a technical understanding, when to use what. We have in-context learning and test time training. Now, you remember my last video I showed you here for this in-context learning, we have a new discovery that we have a phase transition in the learning capabilities, and I showed you the specific parameters that you can apply ICL and not have a fine-tuning that you have to pay OpenAI for fine-tuning their O1 model, for example. Plus, I showed you if we have not in-context learning few short examples, but we go with higher order cognitive reasoning patterns here in ICL, we can have a significant performance jump. And if you're new to all of ICL, this is the video for you. I just show you here that small models have a smarter learning if you are a little bit knowledgeable about how to make them smarter. Now, we have weight tensors here all over our architecture here. If we think about transformer, let's think about transformer first, maybe only about autoregressive transformer. And we have the query weight matrix, the key weight matrix, the value weight matrix, the output weight matrix here with the specific shape, with the specific calculation, mathematical operation. And here I show you here already Gemini 2.0, the Flash. This is a real beautiful brand new LLM by Google, multi-modal. And I just ask it, hey, can you explain here our transformer weight structure, all the tensor structure, the layer structure, how does it work together? And then also, of course, we have to think about the feed-forward layer weight structure and give us here a beautiful refresh so that we are all now on the same level. We understand exactly at what particular matrix operation we are looking for and what nonlinear relay activation function, for example, we will apply. And we have to understand this before we can start with the deep dive of today. So let's talk about here terminology. We have the fixed model parameters of our LLM, and then you always hear activations. What is an activation? In any neural network, activation simply refer to the output values either of a neuron or a more complex structure like a layer after this element processes some input function. If you want, in the simplest case, think of it simply as a signal that is passed here from the input, from the embedding layer, all forward in our different layers here of our neural network, forward in the complete network architecture. This is it. So specifically, if we think about transformer, we can talk about here the activations at every specific different layer, the output that we received on one layer, that is the input to the next layer, each representing here exactly here specific modular values. And as the prompt, you remember our tokenizer, our specific token, flow now through these transformation layers here, specific activation patterns emerges, are calculated by the operation in the transformer, which represent here the underlying information provided by the examples in the prompt. And when the prompt is presented, if you want, you can see it here as a temporary prompt-specific computational graph that is activated and executed here, simply calculating here those activations. Now the interesting part is that we have patterns in the activation themselves. Well, of course. In those patterns here are the result of some complex relationships that are encoded with the trained parameter. I refer here to the forward and feedback loop, the backward calculation, if we modify the weights of an LLM. So there's also here exactly how to calculate now in a decoder-only transformer for an autoregressive modeling, our GPT systems, for example, how to do here the calculation of those activation in detail. And again, I tested out, if you want, Gemini 2.0 Flash here, and I think did a real nice job, the input embedding, the positional encoding, the different decoder layers here, the mask multi-head self-attention calculation, the feed-forward network, the normalization and the residual connection, the skips connection, the output layer. So softmax function, of course. And if we understand all of this, now we're ready to jump into this. Of course, you can have here simple ChatGPT for Omni, the static weight here in a transformer block. You have here the multi-head, then the static weights, here the projection matrix, the key projection matrix, the value projection matrix, the output projection matrix, and then the feed-forward network with the two different layers that you have. And here we already see, if you want, that in a single transformer block, we have some major components here. We have here the multi-head attention here with the static weights, the feed-forward network with these weights here, with the bias here. And we have, of course, a normalization and a renormalization, and so on. Yeah, if you want to have this for GPT-2, the numbers, beautiful. But what I'm interested in, and you ask this here, what is now happening? Where are these induction heads here for in-context learning? And what is an induction head? So to really have a complete understanding, we understand the complete terminology. An induction head is nothing special. Well, it is a special transformer head, if you want, that is activated at a particular point in time if we do in-context learning. So let's see ChatGPT, after I have some hour-long discussion on a feed, I think a dozen of archive paper into this. This is now the result. So this dynamic attention weight calculated during the in-context learning are closely related to the induction head in the transformer block, because induction heads are a specific phenomenon observed here in the attention-based models, and they play a significant role in enabling models to generalize patterns and a better reasoning capability about the input sequences dynamically. So you remember here our test that we have. Also, if you go here to the community tab in my YouTube video, you see I have specific tests for in-context learning, and they are simply sequence-based tests. So let's go here. A sequence contains A, B, A, and the induction head is now the particular special head in your transformer architecture that can learn that the next token after this should be maybe a B. And this induction head emerged during the training as a natural consequence of the model trying to optimize here for general sequence modeling tasks in context learning. However, already at the end of 2021, this is here the first time I found here the mathematical framework for transformer circuits And in their circuit analysis, have a look at this. It's quite mathematically heavy, but they already found here that there are specialization in the attention head happening. And one of this specialization they called here in the publication from March 2022, induction heads. And they found here this close relation already 2022. Can you imagine this? Between the in-context learning performance cycles and dependencies and those special induction head, what they called induction head. So you see, it is all connected. It is just a special attention head. There's nothing additional head configuration happening. This is what the system, the architecture, in its generalization and specialization simply generates here specific heads. And if they have here this particular learning ability, sometimes in the training process, induction head emerge. But they just have a particular specialization. That's all. Great. Yeah, if you want to read here the GPT-4 interpretation of the papers here, great. Yeah, static weights, dynamic attention weight, induction head, how they're all related. If we understand this now, beautiful. So this research here by Anthropic, beautiful papers, have a look at them. This research position here, the induction head, is some really important components here in the transforming the autoregressive models here, particularly in driving here in-context learning through a dynamic pattern recognition. And this phase change that I showed you, this emergent during the training phase change offers here a crucial window into how models develop here the capacity for better advanced reasoning and a better generalization dynamically without updating their static weight tensors, their static parameters of the model. And this is really the main characterization of in-context learning here that we have. There's no update of the static parameter of our LLM. They are frozen. We have frozen parameters of the model, just depending now in the time in the training phase change where we have the phase transition, specific dynamical weight tensors are now performing and super performing, if you want, for reasoning and generalization task. Great. Yeah, I got one question here by quite a lot of my viewers. Is this Grokking? Where is Grokking fitting into all of this schema? Now, easy. Grokking is, if you remember, if we have a beautiful pre-trained LLM, and then just want to indicate here the amount in hours here of fine-tuning. Let's say, I don't know, the pre-training, as shown in my last video, pre-training took close to 1 million GPU hours, and then, I don't know, for 1,000 hours, we had a fine-tuning process already by, let's say, OpenAI or Anthropic or whatever company you like. And what is Grokking? And in this video, I explained it in detail. I show you the effect in detail. It's simply a performance phase of LLMs, but they happen when we say, for example, let's focus here on the fine-tuning process. You remember the researcher who went on holiday and forgot that he had a fine-tuning process running on his computer? So when he returned from the holiday, he noticed, if I've given out this amount of time to the supervised fine-tuning, so far after all here, the overfitting happening here in the training data, if we just give it enough time, suddenly our validation data set reaches 100% accuracy. This is what is Grokking. So if you let go on holiday, let the system run, if you come back, suddenly the system, given enough time, we have now on the new validation data that the generalization, this additional phase of the generalization has entered. But not always. And I showed you here in my video, it is different if you have a known training data or if you have unknown data complexities in your training data set. They will behave differently. So Grokking is here. And yet theoretically, we could, let's say Anthropic or OpenAI or Microsoft could run here real long Grokking phases. But the pre-training of a model is really, really expensive. And the new Llama 3.3 is not pre-trained. They took the old Llama pre-trained 3.1 and only applied a new fine-tuning and then called the model 3.3 with the body, the pre-trained is 3.1. So you see, the costs are extreme, and we are looking for cost-optimized solution. So therefore, yeah, you could also go to OpenAI and pay some, I think, extreme amount of money to have the fine-tuning of their O1 model, of their huge model, for your particular data. But this is in cost relations. I think the Bank of America can afford this, but definitely not any normal company or any normal developer. Therefore, we're looking for better, cheaper alternatives. And now we are here. We are now here with in-context learning and test time training. So you see, we use the model that we have, and we don't have to pay here for supervised fine-tuning or additional pre-training. We are now in the inference run, and now think about O1. Sometimes it takes 1 minute, 30 seconds for O1 to come up with a new idea. This is now this new next generation AI thing that is happening, and it's either ICL or test time training. Now, understanding now in detail ICL, the mechanism when it happened, phase transition, let's focus now on test time training. I already have 2 expert videos. If you start, this is not for you. I show you here test time training adaptation with novel policy reward system in a Monte Carlo tree search algorithm. Too complicated for you if you start. And then I showed you here the test time optimization with an AI reasoning algorithm developed by MIT. Too complicated. Scale inference-based reasoning. If we start, it is so much easier. We just have to know the rules when to apply what and what are the relations between the different elements and what does it mean domain shift and what the hell is a data distribution and why is this determining what of those 2 systems you should use for a better performance of your LLM that is also cost effective. Let's jump into it. Now, the first paper I found here about test time training was July 2020. Here you have the archive link, and this is here beautiful, the authors, and they examined this here and they said our test time training, they called this, is a general approach for improving the performance of predictive models, LLMs, when the training data and the test data come from different data distributions. And they analyzed this, but let me start from the basic. What is a data distribution? Now, a normal data distribution, you have seen this before, no? Or maybe you call it a bell curve or a simple distribution here of data. Let me give you the simplest example I can think of, data distribution. I have here my daylight image data distribution. This is here all the, let's say, 1,000 photos I took with my iPhone in the last days. And you say, okay, so did I photograph a butterfly? Did I photograph flowers? Did I photograph other people? Or did I just photograph some city, landscape, urban scenes and streets and cars and public traffic or whatever? This is my daylight image distribution. Great. This is a data distribution of image data. Wherever you encode it, you have representation. Doesn't matter at all. Here you see I've taken a lot of pictures here from city, from butterfly, flowers, people, and so on. And there I have some images of ants and birds and whatever. Now, if I tell you now I look at my actual nighttime image data distribution. All the images I took after 8 p.m. I have no butterfly images because I can't find them in the night sky, no idea where they are. I have no images of flowers because if it's completely dark, I can't find the flowers. So you see, my nighttime image distribution is different from my daytime image distribution. And some are not even there. And maybe I don't even have a symmetry in my nighttime image distribution because some major blocks are missing from my normalized distribution, for example. So on this simple image, you see my daylight image distribution, or my nighttime image distribution, are shifted, are not identical, are not symmetrical, maybe are not have no other higher symmetries. So I have a shift. And let's say I trained my LLM only on daylight image distribution, and now I want, with the training data set of my nighttime images, to train now, to fine-tune now my LLM for the nighttime images. I have to be aware that there's a shift in my data distribution. So now you understand that the authors here that I just showed you here, they say our test time training is particular if there's a shift in the data distribution. Notice that I did not say that I have now, I don't know, some completely other images. So it's not my image that I take, but those are images, I don't know, from another planet or underwater or some medical images that are not the normal common sense images normal people take. So this is just a shift, but it is not some completely new images from completely new domains. And you see already when we can apply TTT. So we have, if you want, kind of fine-tune, it is a very specific fine-tune, I'll show you in a detail, of this newly shifted data distribution. And we can do this because it's only a little bit shifted during the inference run. So we don't have to pre-train or train it. This is done during the execution of our prompt. Okay, so understanding from the authors of test time training, this is here if we have here a distribution shift, not a completely new domain, because then this approach will fail. We found a new rule. Great. Now you remember here, the very first paper I showed you at the beginning of this video from MIT, test time training for reasoning improvements of our LLMs. And as I told you, they say the most important fact if we have an initial fine-tuning of our LLM, of our small language model maybe, on similar task. So you see the data distribution of our training data has to be in a direct relationship to the given task if we have an inference. So similar means maybe a little bit shifted in the domain knowledge, but not completely new task. Great. So now you understand that the test time training approach is directly related to the fine-tuning that happened to your LLM. If in your fine-tuning dataset of your LLM or small language model, and hopefully you have access, transparency, what data have been your LLM have been fine-tuned on, only when those data are similar to your test time training data in your inference run, then test time training will have a good performance. Otherwise, your performance is worse. You will have hallucination because the systems are not compatible and there's no domain knowledge similarity happening between here the fine-tuned data set and the test time training. We discovered another new rule. And you know what? The third new rule, ICL does not work if we have a domain shift data distribution. Because ICL, as I showed you at the beginning of this video, is working with the frozen weights of the LLM or the small language model. ICL cannot learn shifted data distribution because the weights are frozen. Now I know what you're gonna say. You're gonna say, okay, but then I go back here with, if I know I have a new task like nighttime photography, I go back here and then I do here an additional adapter tuning. So you go there, you pay for an additional fine-tuning for your nighttime images, either in a complete fine-tuning run or in a lower adapter tuning run. And then you have in your LLM the new ability for nighttime images, and then you can use here in context learning for some specific characteristic. Find me the night images of, I don't know, a street where the, I don't know, the light sources have a particular form or shape. Then you can provide here those shapes, those images, those demo images in your ICL prompt, and the system will be able to do it because it has been trained either in the pre-training or in the supervised fine-tuning. So this is now, you have to know here the supervised fine-tuning training data sets, or you simply have to test it out if your LLM is able to do your ICL task, your ICL job, and therefore say, okay, if it's able to do it, I can be quite sure that during the fine-tuning, the data set is compatible, has a similar distribution, or maybe just a slight distribution shift in the data distribution compared to my ICL examples. So now we found a new rule when you should use ICL or not. So therefore, it is best if you have a pre-trained model, take it, only the base model. You do, for if you know your task that you want to do, let's medical imagery or whatever, then you do the fine-tuning. For the small, you pay once every year the fine-tuning process and a cloud provider, but then you know exactly if you have new ICL task in the inference run that you have a coherence, a slight data shift only, and ICL will work. Otherwise, it will not work simply because the data distribution, the domain shift is so massive, no chance that with frozen weight ICL can do the job. Now we understand why it's happening and why sometimes it's not working. So, achieving here this domain shift adaptation during the test time training data, this particular fine-tuning, yeah, I have to show you this. It is not a full fine-tuning. Please, we're in the inference run. We only have 2 minutes, so we can't start here a complete fine-tuning process. So this is called the test time training fine-tuning process. Involves selecting which static tensor structure of our LLM we're going to modify. And now you understand why in the first 5 minutes of this video I showed you all the different weight tensors that we're going to encounter, because now we're going to select only specific tensors. And this decision depends on the specific characteristics of the domain shift and the model architecture. Beautiful. This distribution shift, this data, is so important if your model will work or not. ICL will work or TTT will work or not. So domain shift occurs when the test data distribution differs significantly from the training data distribution. This can be, if you think about writing, either your style, how you write, the vocabulary. Maybe you have a technical vocabulary. Maybe you're a theoretical physicist, or you are, a specialist in medicine. Your vocabulary will be different. Or you have task-specific feature. In all these cases, you have a data distribution shifted. And then T3 will work for you. Test time training will work for you. ICL, maybe not. Great. So, test time training is a process where a model parameter adjusted during inference, during the test time run, to improve the performance on your specific task. And unlike full model fine-tuning that takes 1,000 hours, you just have 2 minutes to do this in the inference. You do not update all the layers, but now comes the beauty. You select, based on your task, which tensors, in which architecture, in which layer of your transformer you want to modify. So, test time training usually focuses on updating only a small subset of parameters. It is not like LoRa that you have a complete adapter. You really go into the architecture, so you kind of have access to this architecture. Otherwise, if you only have a black box, you have to build a little AI system yourself. I'm going to show you this. So, focus on updating a small subset of the parameters in the layers. So either you go to parameters of a single layer of your open architecture. For example, you go a feed-forward network, or you go to the attention layer. It depends on your task. I'll show you this. Or a specific set of weights, like the output projection in the attention or in the biases. So let's have a look at this a little bit more closer. In T3, in the test time training, when the model adapts to a specific task, by your task, your unique task, your unseen task, by selectively updating here the static weights in the transformer architecture using gradient-based optimization, forward parse, backward parse, backpropagation. This limits the adjustment and might involve fine-tuning only specific layers, for example, only updating the feed-forward network weights W1 and W2 and the biases, while keeping the attention weight tensors frozen. Parameter efficiency, by focusing updates only on a small subset of the tensors, the model minimizes simply the computational power that it needs, the overhead, and prevents also, this is the good thing, overfitting to the test data. So we are not even close to coming to grokking, because even before it starts to overfit, we kill the process. Great. And as I showed you here, in the test time training, optimization occurs here in the forward and backward loop for a specific subset of the static weights that you choose. And it balances here the adaptability and the computational cost and the generalizability, the forward parse, the backward parse, the compute the gradients with a specific loss function. And this all has to happen, let's say, within less than 2 minutes. So you see, TTT, now you have to be really fast in your calculation. But you see, even if you calculate here a new loss function, it's rather simple. Have a look at this formula. Great. Now, let me show you here this most simplified code implementation for test time training. You have here your classical transformer block, your forward, your initialization. You define here the loss function. You have here the input. You have your forward parse, your loss calculation, and the backward parse and the optimization process. And you immediately understand that this loss function now compares here the model prediction with the target and calculates the gradient for only some selected weights. And in the optimization, you have here that you only take care about the feed-forward network weights are updated here during the test time training. So you selectively, knowing here the nature of your task in the test time training, you choose now strategically which tensor structures you want to touch in your transformer architecture and modify to get the best performance increase. So, which are those tensor structures that you can touch during T3? You have the feed-forward network weights, you have the attention weight of the transformer itself, of the attention layer, multi-head. You have the embedding layer from the input, and you have the output layer. So, what you do now, if you have a particular domain shift, you must know the domain shift in your data to choose the correct one. Let's say you think, if I only modify here my feed-forward network weights, this layer processes here the token level representation after the attention and add a non-linear transformation, a ReLU, for example, to refine here the features. So updating those specific weight structures, these tensors here allows the model to adapt its feature extraction process for the new shifted domain, not brand new domain, careful, while keeping the attention mechanism intact. So your knowledge from the attention, which token refers maximum to what are the tokens, this is unchanged. When should you use this? Suitable for adapting to domains where the local representation of the individual token changes if you have a different text style or a different structure of your text. Then focus here on the feed-forward network weights. When should you modify here the real attention weights here? Your query, key, and value. The attention mechanism controls how the tokens in the sequence relate to other tokens in the sequence. Updating now the attention weights allows the model to adjust contextual dependencies, which is crucial here for slight domain shifts involving here relational changes. And this is the use case if you have a different syntax or if you change the grammar rules. Then you have to modify your attention weights. Risk also, classical, if the attention weight influences the global context, modifying them to a high extreme, you might risk starting to get into this overfitting in the test time domain also. So careful. The dependencies between your pre-trained, your fine-tuned, your DPO aligned, And now your test time training process, there are dependabilities you have to know and you have to adjust to your particular task. When should we modify here the embedding layer? You know what it does? The embedding layer maps the input tokens into the dense vectors. Updating the embedding can help the model align representation of new shifted domain-specific vocabulary or words. So if you are now if you're integrating now a technical report with some very specific technical terms, then you should optimize the embedding layer and maybe something else. So when you use the embedding layer optimization adaptive to new shifted domains with a new terminology, with new terms, or some real domain-specific vocabulary, but for the reasoning part, the attention mechanism, those weights remain frozen. Those model parameters, remember, are not updated here in this T3 kind of fine-tuning process, because this would increase the computation complexity and it would make it longer, more expensive, and we might find ourselves encountered with new problems. And then finally, the output layer. When should you do this? For example, output layer directly maps here the final representation to the prediction classes or the logic for the classification task. So updating this layer helps adapt the model decision boundaries to a new domain, to an added domain. If you have a classification task where domain-specific class distribution shift occurs, and now you do not have only a classification like, I don't know, sunshine, stars, but now you add, I don't know, some rain or snow to the classification. So you see, those are my simple ideas here for new strategies for optimizing here the weight modification during the test time training process. Improve, especially if you're working with smaller language model and you do not have here this huge amount of free trainable parameters, you have to be smart. So understand the task that you want to use T3 for in your inference run. A minimal update strategy would be best, lowest cost, fastest. Maybe only update here the feed-forward network or the output layer to minimize here the computational overhead, reduce the risk of overfitting here. You might have to go for a layer-specific fine-tuning and add a subset of layer most impacted by this domain shift. And you can combine, of course, both, but then be aware that it will cost you more. You will have other coherence features that will come to play. So be careful that the domain shift is really only a slight domain shift. And if you decide the domain shift is a complete new domain, with complete new vocabulary, with a new insight, with a new reasoning logic, if you encounter a new domain, you should think about maybe starting here the pre-training process all over again. Or if you have some similarities in the domain, you can go with a fine-tuning. But remember, even between pre-training and fine-tuning, if you do not have some basic set of coherence, somewhere deep down in the levels, even fine-tuning might fail you. Great. Yeah, how does this code look like? Just ask here GPT-4 Omni here to come up with here this complete code. You see here our transformer block, forward, self-attention mechanism, norm, great, initiate the model, loss function optimizer, and then we go here with the option to fine-tune here the feed-forward network only, or we go here with the option to fine-tune the embeddings and the feed-forward, or option 3, we fine-tune now finally the attention weights. You see, that's it. If you have access to the structure, if it's a transparent model, if it's not a black box model, you can do this, you can play with this, you can find optimization yourself. If you have a black box model like OpenAI O1, you just have to pay OpenAI to do the job for you. So, therefore, if you want my recommendation now here for the T3, if you have a mild domain shift, and whatever this means in your particular domain, I don't know where you are working with, fine-tuning here the feed-forward network weights to refine the token representation while maintaining here the pre-trade attention mechanism intact is maybe the way to go. If you have some significant changes in the syntax or in the context, definitely include the attention weight here in the update procedure. If you have vocabulary specific changes, if you have highly complex technical terms, or maybe Latin or Greek terms in medicine or whatever, don't forget here, update the embedding layer and at least here the feed-forward network. And if you have task-specific output adjustments, you have to fine-tune only the output layer because the reasoning process would not be sensitive to this particular output adjustment. Great. So now this video would stop, but I have some further ideas. So if you're really interested into implementing all of this, ICL, T3, Inference run, if you want to go here to make your smaller language model smarter with not a lot of cost, if you don't want to spend thousands of US dollars here in cloud optimization, how can we go further? And I don't want to fine-tune here the complete model on this distribution shifted data distribution. Yes, of course, I could do this. I could pay OpenAI here for O1 fine-tuning. But what if I have my own small language model? I want to be smart. I want to be local. So my real personal thoughts here to optimize T3 here for shifted domain knowledge. If we go for categories, as I've already shown you here, pre-trained and coherently fine-tuned on finance and healthcare knowledge, let's say that. And now you want to add, if you have the task of predict categories, you want now to add here a new category, technology, as a new knowledge domain for the task. You could fine-tune the complete system, of course, but I think a cost-optimized version would be to go to T3 in the inference run, understand that it's only a shifted domain knowledge as technology. You have technology in healthcare, in finance, and in end. So I would now go forward and I have to do the test myself to extend here the output layer weight structure and the biases to handle here additional classes, additional categories. And I tried not to extend the layer. It was not effective, but if you extend it here, if you give it new free parameters to learn, I think extension is a good way to go. And then you fine-tune only here this extended new output layers using here this new data set from technology where you have your examples. So you have to think that if you have a small language model, you already have, let's say, a dense allocation here of encoded knowledge. So if you really want to have complete new categories that the small language model is able to handle, you have to extend here the output layer structure in some way to give it here a new capacity to calculate here for new categories. Yeah, code is as simple as can be, as you see here. If you go for technical vocabulary, and your angioplasty or myocardial infarction or whatever you have, the model embedding layer in the intermediate representation may not fully capture here the nuances of this new vocabulary. At first, your tokenization might fail, but also if you have the right tokenizer, those words, they have no context relation in the pre-training or in the fine-tuning, then this is a real problem. But let's say you have some basic and you only have a shifted domain knowledge that you want to take care of. What I would do is fine-tune the embedded layer, the embedding layer here to better represent these new terms, these new technical terms. And then don't forget here, you have now to go and fine-tune the attention tensors or the FNN layers here to adjust how the model processes here the relationship, the semantic relationship between those new terms to the already established terms. So unfortunately, you have to go, and now it depends here of the number of the layers. Maybe you just take the 2 last layers. You have to experiment with this if you want to find for small language model the most cost-effective way, but you also want to have a good performance. So you see, there are ways here to go forward if you understand the inner workings here of the test time training of ICL. And now I think today we have this knowledge. And if you apply the knowledge, you can work here for your task with smaller language model and they have the same beautiful high performance, then you would pay here the global corporations 100,000 or millions of dollars. Great. Yeah. Simplest code implementation you can think of. Go to any code IDE. They will generate here for your particular system, for your particular implementation here, the code. It is rather easy because all those models know how a transformer operates. So there you have it. A very short overview here on these new rules that we can apply if we understand the dependencies between the pre-training, the fine-tuning, how this inference ICL, if you can use ICL and test time training, when to choose what. There are interesting combinations where you can go with ICL and have a reduced test time training, maybe in a later video. If you're a subscriber, you will be notified. And this domain shift is the most important factor here if you can go with an ICL or if you have to do this test time training. How fast you can do this, how reduced you can do this, how selective you can have access to your transformer architecture, to your layers, to your feed-forward network, to your output embedding, and. So the data distribution, the data quality is now so important to understand these new rules, how to get the best result out of your small language model. And therefore, you have to understand here at least the data set and the transparency. You have to have the transparency to understand on what data set here the fine-tuning process happened. And this would be here kind of an optimal system to go to this next generation AI that we expect here a better performance in 2025. This is it for today. I hope you enjoyed this video the same way that I do. Maybe you found some new ideas, maybe you found some new insights, some new rules how to optimize your local system for not a lot of money. And it would be great to see you in my next video.